organized by IABSE. My name is Andrew Orsesi from Cerema in France, and I'm very happy to be moderator of this webinar today. Just some information, this webinar is recorded and it is also being streamed live in the IABSE YouTube channel. And after it will be put on the IABSE e-learning website. I will share the screen to say a few words about IABSE. I hope you see my screen. So the mission of IABSE, with over 3,200 members in more than 100 countries, is to exchange knowledge and advance the practice in structural engineering worldwide. So in fact, it is not only bridges, but in fact, all types of structures and structural materials and all aspects of the construction process are covered in this association. You see the leaflet of the webinar today, so it is also part of IABSE to organize such event where we provide a forum for discussion, for technical discussion on structural aspect. Among the other events, so you have several webinars, other webinars that you can check on the IABSE website, and also some conferences. So there was recently previous event, and the next ones are in New Delhi in September. There will be the IABSE Congress on the topic of engineering for sustainable development. And also in 2024, there will be the IABSE Symposium in Manchester, UK. You can, for this symposium, submit some abstracts now. There are also some publications by IABSE, like the journal Structural Engineering International, some bulletins that investigate some particular topics, or the proceedings of the congresses, as you can see here, the last one in Nanjing 2022. Also some bulletins that investigate some particular case studies, like the one about the collapse of the Chirajara Bridge in Colombia. IABSE is organized with national groups and task groups. So in several countries, you find an organization of this association where the people meet and discuss about technical topics, and also the concepts of task groups. Like our task group today that organizes this webinar is the task group 1.3 that belongs to the technical commission 1. You can see here the 6 technical commissions of IABSE. And in fact, a task group is a kind of mini committee where the people work on a specific topic, and they have some, they identify a period in which they try to reach some particular objectives. I should mention that there is a Young Engineers program at IABSE, and it is particularly interesting for young engineers to have access, to have special prize for when they for membership, and also to have access to some documents. And it is a good chance for them to start meeting international experts. Here you see some examples of the events organized at the national level, like seminars, workshops, or technical visits. So you can check more about this on the IABSE website. Also, you can find some information about a lot of materials, webinars and keynotes that are available on the IABSE e-learning. as the webinar today will be put on this website after today. And after this short introduction of IABSE, we come to the introduction of our webinar today. And the topic is the assessment of existing bridges based on recent guidelines and standards. And we have 4 speakers today. We will start with Professor Dimitris Diamantidis from OTH Regensburg in Germany. And he will provide some technical background about the verification formats. Then we will have Dr. Fabrizio Palmisano from Politecnico di Torino in Italy, and he will provide some information about the second generation of Eurocodes and the part dedicated to the assessment of existing structures. Then Dr. Miroslav Sikora from CTU in Prague, Czech Republic, will present an overview of the developments in the FIB Model Code 2020. And finally, Professor Alan O'Connor from Trinity College in Ireland will detail a probability-based assessment framework and how it is applied in Denmark. Just to mention that this is today the first webinar of a series of 2 webinars, and there will be another one on June the 9th this year. So you can check the IABSE website and register. This second webinar, we will have a look at the practical case studies and how we can implement such approach when we want to assess existing bridges. So I will stop sharing now. And before we start, there will be a Q&A session at the end of the webinar. So if you have any questions, just check the Q&A control button in Zoom and put your questions there, and we will address these questions at the end of the webinar. And with that, I will give the hand to Dimitris. Dimitris, you can unmute and share and start your presentation. Yes. Yes, we see it now.
Okay. Thank you, Andre. Good afternoon, everybody. I'm glad to be here with you and talk about concept and framework of assessment. And I would like to focus on some issues. First one, definitions and procedures. Second one, updating of information. Then we need that to go to the verification formats mentioned before. And then I would like to touch safety acceptance criteria. So I would like to go first on definitions. And we know that the risk is a product of 2 parameters. The one is the probability of collapse, the probability of failure of a member of the bridge, and it is defined as probability of exceeding a limit state. The second parameter is the associated consequences. What happens if we have failure? And this can be human consequences, of course, economical consequences, environmental consequences. So it is interesting how to combine them and to put monetary value behind them. The reliability of a member or of a system or of a structure itself is 1 minus the failure probability, and it is the ability of a structure to fulfill all required functions during a period of time under given conditions. And the period of time, it's the design service life, which is 100 years usually for bridges. But we should keep in mind that bridges in average, they don't make 100 years. Due to obsolescence, the experience service life, based on several statistics, they are less than that, maybe 70, 75 years. Keeping in mind these definitions, we can also have as a measure of the reliability, the so-called reliability index, which is Vita here and is directly related to the probability of failure. So if the reliability index is increasing, the probability of failure is decreasing. It's a simple measure suitable for engineering purposes. And these measures are already implemented in the standards and guidelines we are going to discuss today. It could be also interesting to see the experienced human risk in bridges if we plot the frequency of accidents with N or more fatalities per year and the number of fatalities on the other axis. You see here 1, 10, 100 in a log-log scale, as you see. So you can only accept failures, collapses, when they have large consequences, if they have a very low probability of occurrence. So this would be somehow an acceptable domain. The points are registered data worldwide here European data. And these lines, they reflect the acceptability criteria which are behind the Eurocode 0 as interpreted by Brogevich in a study he did. So you can see here the background of risk illustrated in this diagram, for example, which is easy to understand. After the definitions, we have to look at some procedures, because if you do assessment and you verify existing structures, in this case, existing bridges, you have different stages. In a first stage, as it is also adapted here from the ISO standard on assessment, you have a preliminary assessment where you study documents, you look at inspection, preliminary visual inspection, and so on. And it might not be necessary to do a detailed assessment. This is specifically also implemented in several standards. But in case you need to assess specific members where a risk has been identified, you proceed with more detailed calculation, you determine the actions, you do testing, and finally, you do structure analysis, and you have to proceed with the verification of the critical members of the structure. At the end, you have to take decisions regarding what to do, upgrading, repair, or monitor the structure, or even demolish it. So this is a general flow diagram, and you can here see two typical examples of that. One typical example, a railway bridge here in South Germany, where we applied a simple scoring system, giving some scores of the situation, of the condition of the structure, for example, of the foundation, of the corrosion of the steel joints, of the supports for masonry here. Looking also at the steel resistance specified at the time the bridge was constructed, and at the actual traffic condition of the railway. This is a so-called preliminary assessment. Another example is a detailed assessment here dealing with steel road bridges, where we look here in detail at typical image states, which can be extreme load, but also fatigue, which is a problem of steel bridges. By specifying, for example, a residual lifetime, we want to use this bridge for another 20 years, for example, and looking at the possibilities of fatigue, of crack development here in critical joints of the bridge. So we have to develop an analytical fatigue model. We have to look at crack growth, propagation, and at the end, you will come down with some, of course, some safety measures like could be traffic restrictions and so on. So these are two typical, let's say, preliminary detailed assessment as it is implemented in standards. Now, if you go to detailed assessment, I mentioned one very important point, because your structure is existing. It is there. It's not like in design where your structure is only in your head. It is there. So you can go and measure things. You can update. You can actualize your information. For example, in case of concrete strength, you can do destructive or not destructive testing, or you can even do a proof loading of your breach. So there, and check the capacity of the breach. So there are different procedures how to go. You can measure geometries and so on. So you have this effect of additional information, which will help you to update. For example, in many cases, we have a prior information. We know how the concrete strength is varying. What is the statistical distribution for typical concrete production in the area where the bridge has been constructed. And we have this prior curve. Then we get additional information. We do the testing, and we can combine both, and we come down with an updated distribution. So for practical, let's say, implementation, we have a prior here design value, and we will get, based on the new distribution, an updated design value. In this case, I would call it assessment value. So I would substitute this small d with a small a. In case of proof load, this can not only be a proof load, can be the survival of a high load. This is already a good piece of information. You can truncate the distribution, the statistical distribution of your resistance. Typical distributions of resistance are log normal distributions, like here. This is the distribution of the resistance. Now, suppose that we have survived a high load associated to this value. This can be a fixed, but in many cases also a varying parameter. Then we can truncate in both cases the distribution, and we have a new distribution with another mean value, for example, and we have a useful piece of information which can be implemented in the verification. And the verification, now we have the so-called verification formats. And the first and most classical one is the partial factors. We are applying partial factors in both action effects and resistances to verify our members. If we go 1 degree of sophistication further, so we apply a more sophisticated tool, we can calculate the reliability of our member and, as we will see later, compare it to a target reliability, so we can verify by using this method and considering the uncertainties through the reliability index I mentioned in the beginning. In an even more sophisticated procedure, we can include the consequences also mentioned in the beginning, and we can do the decision-making including the quantified consequences. This would be somehow a risk-informed format for the verification. And it can be used in very specific cases. This is a hierarchical procedure which is compatible to the new Eurocode 1990. We and you probably are more interested in partial factors, and this is a classical procedure which is applied. In this case, as I said, we will use assessment and not design values, so the small a. And we have to prove that the assessment value is smaller than the of the action effect is smaller than the assessment value of the resistance. And we will apply partial factor. And there are two possibilities which are mentioned in the standard. The one is we get fixed partial factors. This can be, for example, the same partial factors as in design. This would be a very conservative solution, or a little bit reduced factors as provided in national guidelines, and they are valid for a cluster of cases. Cluster of cases can be, for example, road bridges of consequence class 2. This is just an example. However, based on the information we have, we can calculate the partial factor, and based on the approach, theoretical approach, which is well known, and we can adjust the partial factor in each individual case, which will be better, of course, but it is more time consuming. and it will lead to more optimal solution. And this adjusted or flexible, because it's only for individual case partial factor, it will depend for the target reliability, what is our minimum safety we want, where reduced values can be possible compared to the design. It will depend on the so-called sensitivity factor, alpha, which reflects the influence of the variables on the failure probability, on the reliability, and get values between 0, no influence, and 1, full influence, maximum influence. And they are rules provided also in the Eurocodes. And they will depend also on the distribution type and parameters they update in one based on the information we have got. They are procedures and several literature on that, like the Joint Committee on Structural Safety Probabilistic Assessment of Existing Structures, how to do it, or the FIB Bulletin 80. So in summary, we can see that the three first Greek letters are governing design and assessment: alpha, beta, and gamma. Regarding the target or minimum values of reliability, they are values given in the Eurocode, and they depend on the reliability class. Reliability class 3, high consequences of failure; reliability class 2, medium; reliability class 1, low consequences. And also on the reference period, which can be 1 in 50 years. And the reference period is associated to the target reliability, as mentioned just before, and also to the statistical value of the time varying parameters or variables, like in our case, the traffic load. So one should be careful when he performs the reliability verification. Classical value applied, 50 years and 3.8 in many studies. However, this criteria are a little bit vague. So one cannot classify. There are better criteria existing. So we tried in some studies, or for the development of some standards regarding also bridges, to provide more information on this classification. And this is possible if one looks here at these three bridges. One is a small pedestrian bridge where you walk during a calm night. This is a classical highway bridge, and this is a very important bridge connecting, for example, the two parts of Greece here. So you can put as parameters for the classification the traffic volume or the span length of a bridge, and you can classify here the small bridge as consequence class 1, and this very important bridge as consequence class 3, and you will have different partial factors for the verification of the members of each of them. Regarding the safety acceptance, I don't want to go into too much detail, but I would like to mention three important things. The first thing is that a lower safety level compared to a new structure can be acceptable. And in some cases, also in standards, has been proposed. The second thing is, as I mentioned, there are various criteria, so one can find in the literature or in pre-normative documents different criteria, depending also at the number of persons at risk or the traffic and so on. However, the acceptance criteria or the target reliability, in general, they would depend on the cost of safety, on the consequences of failure, which are also put as a cost, or they get monetary value, on the, in a case of optimization, the desired residual lifetime. However, one should bear in mind that minimum human safety is always required and should be fulfilled. So this is the background. We might get the same, but it is possible also to get different minimum reliability levels in the assessment. So I would like to conclude in this really a very short summary of the background. I hope I gave you some basic ideas. You will get some more numbers later on. Just mentioning that we have concepts. They are reliability-based and risk-informed methodologies which can be used. important is to apply and use the additional information, depending, of course, on the budget you have available from your structure, from your bridge. And then regarding the verification format, the first format you apply are the partial factors, which can be fixed or adjusted, as mentioned in the beginning. And all these steps have been implemented in the new generation of the Eurocode, as well as in the FIB Model Code 2020. And I close with two pictures from a bridge, which is in the city I'm teaching. It's Regensburg in South Bavaria. It's on the Danube River, and you can see the stone bridge built in the 12th century in a floody condition of the Danube River, but also in a nice night calm condition on the right side. I thank you for your attention, and I pass the ball back to Andre, possibly, and then to Fabrizio. Thank you very much.
Thank you, Dimitris, for this very clear presentation of the different verification formats. And I think we have the good transition with the two following presentations. So first, Fabrizio, you will introduce the new generation of Eurocodes and how it is dealt with for the assessment of existing structures. And then after, we'll have the presentation of Mirek about the FIB Model Code 2020. So Fabrizio, if you want to start sharing your screen, and then after you can, yes, move on.
Yes, sure. Thank you very much, Andrea, and thank you also, Dimitri. And good afternoon, everybody. We'll talk about the second generation Eurocodes and some key points relevant to the assessment of existing structures. I'm here not only as member of task group of 1.3 of the IABSE, but also as member or leader of some project team devoted to the second generation Eurocodes. As you probably know, the current Eurocodes are used not only in Europe, but also in many other countries. They are adopted outside Europe or in process of adoption. The current Eurocodes is composed of 10 Eurocodes. EN 1990 relevant to general rules, EN 1991 Eurocode 1 relevant to action. Then we have the material specific Eurocode, Eurocode 7 devoted to geotechnical design, and Eurocode 8 devoted to seismic design. In the current Eurocodes, we have an assessment and retrofitting part only relevant to seismic action in Eurocode 8 Part 3. In 2010, the development of the second generation Eurocodes has started huge programs that has involved more than 1,000 experts, and that will be completed with the withdrawal of the first generation Eurocodes and the conflicting document, national document, in 2028. The second generation Eurocodes will be composed of the same Eurocode as today, but new parts, new improvement, etc. There will be two additional Eurocodes that so far are in the form of technical specifications, so just a lower level, a bit lower level. One relevant to grass structures, one relevant to fiber polymer structure, and one relevant to membrane structure. We have for sure, regarding to existing structure, the assessment and retrofitting part relevant to seismic action in Eurocode 8 Part 3, but we have also new part. We have in EN 1990 Part 2 relevant to general rules on assessment of existing structure. We'll have an Annex I in Eurocode 2 devoted to assessment of existing concrete structure, and we'll have also an annex in Eurocode 1 relevant to actions during structural interventions on existing structure. However, I will talk just a bit because of time constraints, giving some key points that are relevant to the activity of this task group regarding the EN 1990 Part 2 and Eurocode 2. Let's start with the EN 1990 Part 2. The main challenge of this Eurocode was that different countries developed in time different products, approaches, and codes of practice. irregularities. So this new Eurocode should account for all these differences that in many cases are very important, and should give countries a wider possibility to add specific rules for different peculiarities. This is why there is a wider use, when compared with the other Eurocode, of the so-called national determined parameters that are specific numbers given for specific parameters that could be given in the national annex by the national authorities. However, in this Eurocode, we have a wider use, so we give also the possibility to use them for general provision. For example, to better define what is an existing structure, because the definition in different countries can be very different, and there are some legal matters to be taken into account. Part 2 is the development of the technical specification published by CEN in 2020, and it gives additional provision to Part 1 to cover the assessment of existing structures, including geotechnical structure, and the general principles for intervention. So this is not a self-sounding document, because there are many rules that we use commonly for the design of new structure that can be also used for the assessment of existing structure. Part 2 does not provide provision for seismic assessment and retrofitting of existing structure, because historically and in the second generation Eurocodes, they are included in Eurocode 8. We have also in this code, as mentioned by Dimitris, a flow chart proposed for the assessment process. And for each stage and step of this assessment process, we have specific rule and provision. I don't have time to go into details. However, it is defined that the assessment process, as usually made, is a stepwise process with increasing levels of detail and accuracy. We in general start with the preliminary assessment that in general is very rapid, with some inspections, some slight calculation, etc. And then we decide if we will go through one or more stages of detailed assessment. At the end of the process, if the structure satisfies the reliability level given by the code, we can complete the assessment. If not, there is the need to make some proposal for interventions. And in this code, there are also some specific provision given in the main part as well in a new informative annex relevant to intervention. There is also the differentiation of the intervention, for example, construction and operation, and for each of them, there is a differentiation of the kind of intervention. But how to deal with the assessment? What methods of assessment we should use? There is a quantitative assessment method that is recommended. This is the only method recommended. This is based on calculation, and it follows all the steps and provision included in the entire Eurocode. However, in some cases, we can use, and it is permitted, qualitative assessment method together with or in place of quantitative assessment methods, but only where conditions of use are met. And these conditions of use are different from country to country, and so they are given in the national annex. However, additional criteria for the use of qualitative assessment methods should be also specified by the relevant authorities or parties involved in the assessment. And it is also stated that qualitative assessment, as usually already made, can be used for example, to assist the definition of the assessment scope and objectives, and also for the very first preliminary part of an assessment process. If we move to the verification, we have only one recommended format, that is the so-called partial factor method, because as in part 1 of EN 1990 for new structure, this is the only method that should be used for both new and existing structure. The great difference is that for existing structure, we have the possibility to use, in addition to the partial factor method, either the reliability-based method and or risk-informed method, to better have an evaluation of the reliability level of the member of the structure. The basic format of the partial factor method is the same as the one used for the new structure. However, as shown by Dimitris, there is also in this code the possibility to use either fixed partial factors or adjusted partial factor. And the fixed partial factor are in general standardized for use in a country. They are valid for a range of cases. And in general, So far, they are the same as new structures. However, adjusted partial factor can be used if given by the Eurocodes or specified by the relevant parties for specific cases. And when dealing with adjusted partial factor for action, this should be given the national annex relevant to this Eurocode, because EN 1990 gives the partial factor for actions. However, for materials, the relevant adjusted partial factor should be given in the material-specific Eurocodes. And for the time being, we have specific rules only in the Eurocode 2 devoted to concrete structures. The basic formula to be fulfilled for the reliability-based method are these two in the top of the slides. The verification can be made verifying that the probability of failure should be not greater than the target probability of failure, or the reliability index should be not lower than the target reliability index. Everything in the given reference period, where the reference period is defined in the code as the period of time that is used as a basis for statistically assessment extreme realization of valuable action and possibly for accidental actions. In the code, we can use either the 1-year reliability index or the 50-year reliability index. There are only in Annex C of Part 1 some suggested values for new structures that can be used also in general for existing structure, but they are NDP, so the national annex can modify or give additional values. However, we should mention that if we use 1-year reliability index, the target should be met for every year of the required or choosing remaining service life of the existing structure. Target reliability level for existing structure or rehabilitated structures can be lower than that for new structures because the relative cost of safety measures to increase reliability is greater than that for a new structure. And we have to keep in mind, and it is specified in the code, that the target reliability should take account of many parameters, many factors, including the possible cause and or mode of attaining a limit state, possible consequences of failures in terms of risk to life, injury, potential economical losses, cost of safety measures, as I mentioned before, and public aversion to failure. But this is a matter of national authority, because only national authority can define the target level of an existing structure. So this is not a matter of the assessor. The assessor cannot define for each structure what is the target reliability level. Let's move quickly to concrete structures, Annex I, assessment of concrete structure. Annex I gives some additional rules for material and systems, gives additional rules for assessing existing structures where detailing does not comply with the provision value for new structure. And we have many cases because details used commonly in the past are completely different in many cases from that used according to the new standard of practice. Additional rules for anchorage of plain bars, because plain bars cannot be used according to Eurocode anymore for new structures. So there are specific rules according to new development in the literature for the anchorage of plain bars. Some general considerations and provision for the deterioration of existing concrete structure. There are not specific model for deterioration, but only, as I said, general provision. So I will talk briefly, mainly about the partial factor, the adjusted partial factor. And I want to mention that there is in the Eurocode 2 a strict correlation between what included in Annex A and what included in Annex I. Annex A gives a general procedure to adjust the partial factor for both new and existing structure. However, in Annex A, this procedure is a permission, it's not mandatory. The formulation of the gamma factor for material, concrete, reinforcement steel, and this is due shear verification because it's different, is the one that we have at the top of this slide, sorry. The variables involved are strength, model, and geometrical uncertainty, and the general assumption is that they are log normal distributed and statistical independent. And this formulation is a function of the sensitivity factor for resistance, the target value for the reliability index, the coefficient of variation of resistance, and a general bias coefficient for resistance. That is the product of the bias of each parameters involved. I don't have time to go further in details, but I want to mention that all the details on the procedure included in the Eurocode will be given in the next webinar on the 9th of June with an application to a real case study. As I said, in Annex A, there is the permission to adjust the partial factor. This is a possibility. However, this is different, slightly different in Annex I when dealing with the existing structure. Because if the coefficient variation of concrete is higher than a given limit value, the coefficient of variation of steel reinforcement is greater than a limit value given in this table, depending on the number of test results made on the existing structure, the adjustment is not permitted anymore, but is recommended. Because if in this case we use the same partial factor as given for new structures, so fixed partial factor, we are not on the safe side anymore. So it is recommended to adjust the partial factor. Another key point that I would like to highlight, and this is the very last one of my presentation, is relevant to the general procedure to obtain FCK. As we know, there is a huge difference between new structure and the existing structure. When we're dealing with new structure, the FCK, that is the characteristic compressive strength of concrete, is obtained by test on sample taken during casting. However, when dealing with the existing structure, in many cases, we have new tests performed in situ, for example, destructive and non-destructive tests. So what we obtain is not FCK, but is a different value, that is FCK obtained in situ, from in situ test. And we have a general procedure given in a European standard, EN 13701. There is the necessity to pass from FCK in situ to FCK, since all the formulae given in Eurocode for both new and existing structures are in terms of FCK, because they have been validated for FCK and not for FCK in situ. This is why in Annex A we have this very simple formula where there is a parameter kappa that is a function of the position of the test of the course, for example, taken from the structure to make all the test and to evaluate FCK. And this we can see kappa varies from 0.85 to 0.95. This means that in some cases, depending on the region where the courses are taken, FCK can be very similar to FCK in situ, while in other case, FCK can be greater of about the 17% than FCK in situ. And with this information, I've completed my presentation, and thank you for your attention. I pass the ball again to Andrea. Thank you.
Thank you, Fabrizio. So I think we see a lot of very important information in your presentation, the importance of the role of the national authorities that will provide values for application, and also how we can have an updating of the partial factors, and also how we can take information from in situ tests. So thank you very much for that. And now we move to the presentation of Miroslav Sikora about the FIB Model Code 2020. Thank you, Mirek.
Thank you, Andre, for a very kind introduction, and thanks Dimitris and Fabrizio for excellent overview of theoretical background and background in standards for assessment of existing bridges. In this presentation, we will focus on FIB model code, which is now in its final draft phase to be voted just in the beginning of June in a FIB symposium. So, assuming it will be approved, there will be a thorough background document which is typically used for development of standards, and in some countries it's directly used by engineers in practical applications. In this presentation, we will just briefly discuss parts of FIB model code focused on reliability assessment of existing bridges. I should acknowledge that This background has been developed by FIP Task Group 3.1, which is focused on a basis for design and assessment in FIP model code, and its main mission is to provide recommended values of partial factors. The other focus is then on probabilistic approaches. It has been already mentioned several times that important part of the whole process to derive partial factors is specification of target reliability. In FIP model code for design, it's assumed or it's applied more or less the same approach as in Eurocode. So it's allowed to use 50-year reference period and take, for instance, for CC2, take the common value 3.8 of reliability index, or it's allowed to apply 1-year reference period for design, and in this case for CC2 structure the value 4.2 is proposed. The small revolution comes with recommendation for assessment of existing structures, including bridges. So if we keep focus on CC2 class, so in this case, the recommendation is to take annual beta of 3.3, and this is the stone from which let's say lower partial factors originate as recommended in the model code. Because our time is limited, so there is several points which are explaining the reasons why 1-year reference period has been chosen for assessment. So if we have time and if there is interest in discussion, I am ready to respond these tasks, and in a similar way how to apply annual target reliability in reliability verification focused on the whole service life. So this is ready for discussion. I would like to point out that I would like to explain how partial factor for concrete was derived in a FIP model code, and in blue bubbles we see assumptions which have been adopted for the phase in design. In gray bubbles we see assumptions which are relevant for assessment. I should acknowledge that the approach for design is let's say fully compatible with the Eurocode, with some small exceptions, but mostly fully compatible. For assessment, we proposed in FIP some further guidance. So immediately comparison of these bubbles shown in this slide, we see that there is immediately difference in considering of compressive strength of concrete for assessment, which is just assumed to be obtained from core tests, and for design, which is based on two main variables. One is compressive strength, which is produced in a concrete plant, and the second aspect is conversion factor, accounting for in situ effects like casting and curing of concrete. If we just look at coefficients of variations indicated in this slide, we immediately see that the conversion factor has a higher coefficient of variation than compressive strength produced in plant. So it means that it's a governing factor, which is, however, not playing a role in the phase of assessment. So there is a significant source of uncertainty, which can be at least partly reduced in the phase of assessment. Another aspect affecting partial factor for concrete is geometry. This is less important, so I will skip it a little bit. And the final important factor is resistance model uncertainty. In in the simplified approach, it's assumed that this variable or this effect can be considered in similar way in design as well as in assessment. The similar hierarchical approach was adopted also for partial factor for steel, so it's again ready for discussion if there is some interest. And now I would like to present some, let's say, numerical comparison. If we derive partial factors based on these assumptions, what is our final benefit and what are warnings which need to be raised before this is fully applied in practice. So first we see that in design, the, let's say, default or the basic alternative in model code provides just the same values as we are used to from Eurocodes, for instance. So for concrete 1.5, for steel 1.15, and then we have some differentiation for specific cases, such as higher execution quality. For assessment, the values, particularly for steel partial factor, reduce rapidly. So we keep focus on CC2. We see that for concrete, there is a small decrease. But what is important for partial factor of steel, it can be reduced down to even 1. I underline that the application of this low partial factor is assumed to be always related to information obtained from sufficient amount of tests on the existing structure. Again, there could be some discussion and arguments whether it's possible to assume gamma S equal to 1, and again, it's ready for discussion if there is interest. And now I would like to proceed with final comparison of requirements in design or in assessment if we are using classical Eurocode partial factors or if we are using partial factors for assessment proposed in the model code. In the first row, we see typical Eurocode partial factors, and in this presentation, we will have a focus on partial factor for steel, so 1.15 in this case, and on the partial factor of for road traffic, which is unfortunately hidden now on screen. I am not sure whether you can see it or not, but for Eurocode, we have 1.35. And then we have 2 lines for model code assessment. The first one is for CC2, annual target reliability 3.3. And we see a reduced partial factor gamma S. We also see a reduced partial factor gamma G, and so on. For the sake of comparison, we will also briefly discuss what happens if we increase annual target reliability up to 3.7. In this slide, we see just a very brief comparison of these 3 different formats or different approaches to assessment. Before we go to details, I should explain what is on vertical axis. It's a load ratio, so basically a ratio between permanent and traffic or wind load effects. And basically, to the left, we have situations where permanent actions are more important. This is typical for rather longer span bridges. And on the right side, we have situations when traffic load or alternatively wind load, just for the sake of comparison, traffic load is dominating, and this is typical for shorter spans of bridges. On vertical axis, we have comparison of requirements. Unity is related to design according to Eurocodes, and the ratio, if if it's the ratio below unity, it means that requirements for assessment according to model code are less than those for design by Eurocodes. So in this graph, we see by red curves, we see results for bending resistance, so mainly driven by properties of steel. Gray curves indicate results for columns, which is combination of effects of concrete and of steel. Bold lines indicate results for traffic load, and just for the case of comparison, thin lines indicate results for wind. What we see immediately is that quite obviously, model code assessment leads to lower requirements compared to Eurocode design. We see roughly that for columns, requirements are at the level of 75 up to 80%, and for bending resistance, we are somewhere around 80%. So this is the effect of mainly the effect of reducing annual beta value down to 3.3. This is one important aspect. The other important aspect is that we are assuming reduced uncertainty about material properties, about geometry for existing structure. Just an information not shown in graph, but if we decide to increase annual beta level for assessment up to 3.7, which can be considered, for instance, for highway bridges. So then these lines indicated in the graph on average increase by about 5 to 10%. So we are somewhere around 85 up to 90% of Eurocode requirements. So we keep in mind that not only reducing target reliability, but also reducing uncertainty in basic variables leads to these reduced assessment requirements. And this drives us to concluding remarks. So I would like to emphasize that there is really full compatibility between new Eurocodes for assessment of existing structures and draft, let's say complete or final draft of FIP Model Code 2020. Important is that lower target reliability levels are proposed for existing structures, including bridges, and fixed partial factors are recommended for conventional cases. I forgot to mention that there are also formulas, there are tools how to derive case-specific partial factors if needed or if wish to do so. Adjusted partial factors can be derived for individual cases, particularly when there are, let's say, overly conservative approximations by fixed values, or when we are analyzing or verifying key members with possibly high failure consequences, in cases of improved production or execution quality, where recommended values, recommended models do not apply. And the last remark I would like to make is related to sustainability. It's believed that it's quite natural, well argued or well justified that lower target reliability should be considered for existing structures. Of course, we always have to keep in mind human safety and check minimum human safety levels. And in case of concrete structures, it seems to be quite obvious that it's not really necessary to require a high gamma value for well-known load, which is a self-weight of concrete. So it's quite even by previous practice in national standards, let's say, it's quite obvious that this value should not be 1.35 in the case of existing bridge, but rather somewhere below like 1.15. So this is the last remark I would like to make. Thank you for your attention, and the ball is again on Andre. Thank you.
Thank you, Mirek, for your very interesting presentation that shows in a quantitative way how changing the target reliability level or changing the variability or the uncertainty level on the variables can change the result at the end. Before I forget, you have a Q&A control button on your Zoom. So put your questions there and we'll address them at the end of the next presentation. So do not hesitate. And now we have Alan that will talk. We come to the level of probabilistic format and with the illustration in Denmark. So Alan, the floor is yours.
Thank you, Andre. So I hope you can see my slides, and I'm going to speak about the application of a lot of the elements which have been spoken to by the other speakers around particular structures in a Danish context, and how this was made operable in a Danish context through a guideline which has been developed for reliability-based assessment of existing structures in conjunction with the Danish Roads Directorate and colleagues in Ramboll and Copenhagen who've led the efforts. I think it's important to point out that the guideline in itself, as I'll come to it, is consistent with the work which has been done in the various Eurocodes and is cognizant of that work as highlighted by colleagues. So what I propose to do is give a brief introduction to the rationale behind why the guideline is developed, then look in some context and relap over some of the aspects of probability-based assessment and give some high-level overviews of some structures where it has been applied. Then I want to look at a particular case study, bridge structure, and show the application and the benefits of the application, and ultimately draw some conclusions around the application of the methodology and what it means. So really, and this is consistent with what's been said by colleagues, that a lot of participants today are probably bridge owners, and bridge owners face common problems around the necessity to reduce spending on existing structures whilst at the same time attempting to maintain an increasingly aging bridge stock. And Dimitris pointed to the age of a lot of the structures which we have when we perform these kinds of assessment. And in many cases, these structures were obviously designed for a loading intensity completely different to the loads that they're subjected to today. And I'll outline the rationale behind the loading basis, which is considered in the Danish guideline. So the question which is posed and which is addressed in terms of the development of the guideline is, how do we deal with aging or deteriorating of structures, which is subjected to loads which are ever increasing and frequencies of those loads which are increasing, where we have reducing budgets available for maintenance, and yet we need to ensure compliance with the codes in terms of the minimum safety requirements as outlined by Mirek and others. So the strategy which has been developed by the Danish Roads Directorate was to develop a guideline for reliability-based classification of existing structures, of the load carrying capacity of existing structures. Now, what's really exciting in this context is that the original version of this guideline was developed in 2004, so almost 20 years ago. But currently, efforts led by the Danish Roads Directorate in conjunction with Ramboll and others, and I know colleagues are on the call today who've led these efforts, is look at updating the guideline based upon the new generations of the Eurocodes in order to take account of developments in that regard. The guideline itself focuses on aspects which have been considered today, like the minimum reliability requirements which are specified, but also gives us tools in order to deal with model uncertainties, in order to categorize loading in a statistical sense, in order to categorize the performance of varying materials, be those steel, reinforced concrete, pre-stressed concretes, and also gives us information on what Dimitris spoke about around updating of parameters in the assessments. It also looks at, in the updated version, it looks at the new fractals which are associated with material characterization. It looks at load modeling. It looks at approaches to reliability-based assessment. It looks at how we model the dynamic amplification factor in a statistical sense. And again, updates to allow for incorporation of model uncertainty. So all of these aspects are dealt with in the guideline, and guidance is given on how to consider them in a coherent and robust sense. So this has been touched upon by the other speakers in terms of the reliability requirements which are specified, and Dimitris went into some detail around the beta value which we require versus the target values, and linking those to consequence classes. And in addition, within the guideline, it links to the kind of failure mode which we might consider, be those ductile failure modes with remaining capacity, or ductile failure modes without remaining capacity, or brittle failure modes, and what are the necessary target safety levels that we need to consider in that regard. So really the approach is one, as highlighted by the other speakers, around a generalized approach that traditional codes take in the partial safety factor format to an individual approach, where we know that the general approach is conservative, but it's easy to use and easy to apply. It's very generic in terms of the load magnitudes which are specified and the partial factors which are specified. The advantage of that is that it's easy to use, but the drawback is clearly that it's costly, both in a monetary sense, and also, as Mirek just highlighted, from a sustainability perspective, in terms of carbon costs associated with interventions on serviceable structures, existing structures. So really the idea behind the application of the guideline is to demonstrate that we can satisfy the target safety levels as prescribed by the codes, and to consider structure-specific modeling of uncertainties around load and resistance, and not compromising the safety level which is required, but rather optimizing to that safety level. So I could present a myriad of examples, example structures where the methods that have been outlined have been applied, and those could be road bridges, could be rail bridges, can be land bridges, can be sea bridges, can be bridges of varying structural form, can be bridges of varying length. But what I've chosen is a number of high-level examples here to give you initially to demonstrate the application of the methodology, the issues which were faced in the deterministic assessment, and how these were overcome in the probabilistic assessment. So 4 high-level structures which we can look at. First of all, we can look at the Klotoft bridges, for example. And these are beam and slab bridges located in Denmark, built in the 1970s, 4 continuous spans, precast, pre-stressed, inverted T-beams with in-situ slabs. The spans are low to medium length, from side spans of the order of 10 meters to intermediate spans of the order of 25 meters, and the width of the structure being 36.1. I show you the shear reinforcement down here because the issue with this structure, as I'll highlight in a moment, when we looked at the critical limit state, was associated with the shear capacity of the structure. And I'll come back to that in a moment. We can look at concrete arch bridges. So Vilbo is a concrete arch structure, reinforced concrete arch structure built in 1932, had quite a heavy skew at 56 degrees, a clear span of 23 meters, a height of 3.2 meters, 9 meters wide, arch thickness varying from 0.3 meters at the crown to 0.6 at the base. And as we see often when we assess existing structures, this structure was renovated in 1986, and so the aspects of the renovation were considered. The issue here were issues to do with the foundation and the footing capacity of the structure. Wilbyhavn is a simple slab bridge located outside Copenhagen. Again, it's a nice example because it's a very small structure, which we would consider in monetary terms would be relatively inexpensive to replace. But when we factor indirect costs associated with the traffic management activities and the delays which would accrue on the motorway, there's a definite desire to avoid any unnecessary closure of a structure like this. Built in 1942, repaired in 1962 with a wide edge beam added. Again, relatively heavy skew and an arch and a slab thickness of 0.4 meters. And finally, Nustelvej, which is a post-tensioned slab bridge built in 1959. The spans range from 6 meters at the side spans up to 17 meters in the center. Again, a relatively heavy skew. The width of the structure is 28 meters, and transversely the bridge is supported on 10 columns at just above 3 meter centers. The issue here was in the edge columns in the emergency lane to do with the loading case, which was considered. Now, just before I go into the outputs of the deterministic assessment of these structures, I should point out that the desire for each of these structures and for the structures for the Danish Roads Directorate is that they would achieve a class 100. Now, class 100 essentially means that the structures can carry in normal passage a 100-ton vehicle with a standard around 50-ton vehicle moving beside it in unobstructed passage. So here in the figure you can see, and in the table associated, you can see that Clotofta could achieve a 50 capacity rating, which means 2 50-ton vehicles beside each other, located anywhere on the structure. Avilbo could achieve a class 50. Similarly, Rugby could achieve a class 70, and Nustelvai could achieve class 80. So in all cases, the structures failed to demonstrate the capacity which was required for them. So the option here was, on the basis of the deterministic assessment, the partial safety factor assessment, was to move to strengthening of these structures. A decision process was put in place whereby it was determined advantageous to move towards a probabilistic assessment according to the Danish Roads Directorate guideline to see if adequate capacity could be demonstrated for these structures. As I said, in the context of Clotofta, the critical limit state was ULS beam shear capacity. In Avilbo, it was ULS footing bending capacity. In Rugby, it was ULS slab bending capacity. And in Nustelvai, it was the hogging moment in the outermost column, which was in the emergency lane. But again, as I said, the vehicles have to be able to move anywhere on the structure, so they have to be able to move in that emergency lane location. So in all cases, probabilistic assessment and modeling was performed, looking at alternative levels of sophistication in terms of the capacity models which were developed, from looking at using crack slide theory in combination with response surface modeling to look at the shear capacity of the Clotofta beams, developing a response surface modeling for the Avilbo arch, where we considered, in addition to stochastic parameters around the concrete strength and the yield strength of the reinforcement, looking at the soil bearing capacity and looking at the density of soil, which obviously can be an advantageous factor in the context of an arch structure, through looking at Rugby and looking at plastic modeling of the capacity of the reinforced concrete slab, and training a response surface to look at the moment capacity in the post-tensioned Nustelvai case, again, trained using the stochastic variables for the structure. So in all cases, it was required to demonstrate that the target beta, or that the actual beta level, was above the target level of 4.75 for these structures. And in all cases, that was documented. So you can see here the beta value, which was determined. So in the case of Clotofta, for example, a beta value of 5.7 was determined, which was in excess of the 4.75 value, which was required. In all cases, as Dimitris indicated in his presentation, we looked at the importance factors for the modeled variables and looked at the distribution of the importance factors. We also looked at sensitivity analysis in all cases to ensure or to ascertain the sensitivity of the computed beta value to the modeling of the variables, and to satisfy that we had adequate capacity in all cases. So again, through making operable the kinds of techniques which the other speakers have spoken about, through the guideline, which is consistent with the Eurocode formats, we were able to document adequate capacity of these structures and avoid costly replacement. That could be in terms of direct costs or indirect costs, and also enhance the sustainability of the solutions which were presented by avoiding unnecessary CO2 generation through documentation of adequate capacity of serviceable structures. So I want to show you another example from the perspective of the application of the methodology. And this is the Westmotorveien Bridge, which is a bridge constructed in 1965, has superstructure span configurations as indicated, varying from 16 meters up to 32 meters with a total structure length of 97 meters. Again, a relatively heavy skew at 38 degrees, and again was required to document a class 100 rating for the structure. The problem, as you can see in the photograph here, there's an emergency lane on the structure. The problem is when the class 100 vehicle is located in that emergency lane in a torsion limit state case. And the structure was unable to document adequate capacity in that regard. Again, there are number 4 notional lanes on the structure as indicated in the figure below. So the classification was performed according to the 2017 revision to the Danish assessment guideline, which requires, and I'm sorry for the Danish in this, for Danes on the line, they can read the Danish. And for those of you who aren't Danish speakers, I'll explain that the classification required a partial factor of 1.25 times the dynamic factor to be applied to the class 100 vehicle or the 100-ton vehicle, and a partial factor of 1.05 times the dynamic factor to be applied to the class 50 vehicle, which was located beside it. And in addition to that, there were the permanent loads, for example, acting on the structure. The critical location, as can be seen here, is in the location of cross-section 4 and 4A on the structure. And again, that occurred in a torsion limit state. And it also indicated on the slide are the configurations of the class 100 vehicle and the class 50 vehicle. I should have said that the rationale behind trying to ensure that motorway bridges can achieve a class 100 rating is to make simple the permit issuing process, because if a structure is documented to have a capacity for 100-ton vehicles, then permit issuing is obviously a much simplified process for the structures. So as I said, the structure was assessed for a variety of limit states. The critical limit state in the deterministic assessment was found to be the torsional limit state. And I've indicated here the kinds of factors which were considered when modeling the torsional limit state in terms of the shear capacity around the, in terms of torsion around the steel and the concrete, also the cotan of theta and the values associated with that, which we're familiar with from the Eurocode. So it was again decided that it was appropriate to perform a probabilistic assessment of the structure. We performed a wide variety of sensitivity calculations in the context of assessing the structure, from looking at positions of vehicles on the structure, through looking at the influence of the modeling of the model uncertainty for the structure, or for the loads acting on the structure, through, and I've included this slide here because it was referred to by some of my colleagues in some of the presentations, around strength of the materials and characterization of strength of the materials. And what we can see here is that where we worked off information which we had from the original documentation around the structure, around the strength of the concrete, for example, we achieved a beta value which was below the target level. So we performed sensitivity analyses to see how that value varied as a function of alternative values for the characteristic strength, or the mean strength, I should say, of the concrete as considered. And we can see in the table how the beta value varied as a function of the mean strength for the concrete as modeled statistically. And this pointed to an advantage of the method which we can take account of here, which is it indicated to us the kinds of tests which could be performed on the structure to characterize the performance of the material, to update those material models, and to gain a better understanding for the capacity of the structure. So as was indicated by Fabrizio, in terms of the in situ testing which can be performed, in situ tests were performed to assess the strength of the concrete via taking cylinders from the structure, and using that information we were able to, as Dimitris pointed out, we were able to update our characterizations of the modeling of the concrete strength to give us revised values for the mean value and the variability associated with that mean value, which we consider in performing the probabilistic analysis of the structure. And the outputs of that, or the results of that analysis, was that we were able to document that the structure had adequate capacity in terms of a beta value being above the target level for this structure at the critical limit state. And we were able to not only ascertain those values, but also we could perform a sensitivity study, we could, and if you look at the pie chart, we could see what the importance factors were. If you look at the sensitivity study, which is shown in the middle of the slide, we can see what the influence of the modeling of the parameters is on the computed beta value. We could also see in the table in the bottom right hand corner of the slide, we could see the values of some of the variables which were determined at the beta point from the assessment of the structure, and we could compare those to the values which were considered in the deterministic assessment. All in all, we were able to demonstrate that the structure, sorry, just before I jump on from that, all in all, we were able to demonstrate that the structure had adequate capacity. So to conclude, and drawing together in the variety of examples which I've presented, the application of these methods in the context of the new Eurocode for assessment of existing structure, or in the context of the Danish guideline, which is consistent with that Eurocode, is that where we have a failure to document adequate capacity of existing structures in deterministic assessments through deteriorating structures or increasing loads, then we have a clear motivation here to apply probabilistic methods to better assess the capacities of those structures. And those motivations can be both in terms of economic costs associated with the avoidance of direct or indirect costs in terms of the replacement, but more and more in conversations with bridge owners and network managers, the motivation comes around CO2 saving and optimizing the sustainability of existing structures. So what I've tried to do is present you with a number of case studies to demonstrate the application, the practical application of probabilistic assessment to existing structures. In the cases where sufficient capacity could not be demonstrated in a deterministic assessment, the probabilistic methodology has been applied to optimize and avoid or avoid costly rehabilitation processes. As highlighted by my colleagues, we work off target safety levels, so we never compromise the safety of the structure, rather we perform a bridge-specific assessment. The justification for the application of the methodology is provided, amongst others, in the Eurocodes. There are no practical or technical obstacles to applying these methods, as we've demonstrated here. A clear advantage lies in the application or in the incorporation of bridge-specific information and in identification of the value around bridge-specific information and its gathering. And essentially, we're not reducing maintenance budgets, rather we are optimizing them for existing structures. And we are also optimizing sustainable maintenance of existing bridge stock. So with that, I'll thank you very much for your attention, and I'll hand back to Andre for any questions to the presentations today. Thank you.
Thank you, Alan, and congratulations for your very interesting presentation that shows that a probabilistic safety assessment of an existing structure is possible. So let's now open the Q&A session. I can read a few questions, so do not hesitate to put your questions and we'll address them now. So the first question by Juan Ekag is for you, Dimitris. You talked about the definition for the risk, and Juan is asking, he says that in Canada, they consider a third variable for risk assessment, which is detectability. And then they multiply the probability by the consequence by the detectability. And then they can have some mitigation for inspection or monitoring, or even accessibility improvements and minimizing the risk while not modifying the consequence, neither the probability of failure. So do you have any comment and about standards and how this definition is used in different countries or not?
Okay, thank you, Juan, for the question. To my knowledge, at least in the standards I have been working with in the last years, we don't have directly an implementation of the term detectability. However, one does a reliability analysis and calculates the probability of failure, and even later on at the risk analysis, you have the possibility to include the probability that you have not detected, for example, a crack, or you have not detected a damage. And then you can directly deal with this problem in your calculations. However, as it is done in Canada, to my knowledge, there is no direct implementation of this concept you are mentioning in your question.
Thank you, Dimitris. There is one question for you, Fabrizio, still by Juan. So you showed in your presentation kappa values for concrete. So the question is there any kappa factor for steel rebars? The variability for concrete compressive strength is different than rebars, so shouldn't it also be another kappa factor for steel rebars?
Thanks for the question. The variability of strength of both concrete and steel is taken into account in the characteristic value and in the partial factor. So when we update the partial factor, we consider also the result of the coefficient of variation taken from the in situ test. The aim of the kappa value is different because the kappa value considers the difference in resistance if we have a sample taken in situ and a sample taken during casting, because in situ we have the effect of curing, the effect of different curing, of consolidation of fresh concrete, the anisotropy, the effect of coring that we don't have on the sample that we take during construction. So there is the need to have a kappa value for concrete, and we don't have the need to have a kappa value for steel. So the response is that we don't have a kappa value for steel reinforcement.
Okay, very clear. Question by Ian Ferguson. I think Fabrizio, you can still also address. Have you any comparisons being carried out to compare the results from existing standards with the new EC assessment code? And is the Eurocode likely to be more or less conservative?
Thank you. Interesting, this question. The basic aim of the code, as also mentioned in other presentations, is to remove unnecessary conservatism present for new structure, for example, and also to consider the difference between structure built in the past and new structure. So in general, there could be differences in one direction and the other direction. For example, if we adjust the partial factor because we have a very low coefficient of variation, we remove unnecessary conservatism present in the code. However, we can have just the opposite, because we can have an increase of the partial factor if we have a higher coefficient of variation, greater than that used for existing structure. The same we could have for specific rules. For example, when we talk about plain bars, the anchorage of plain bars, we have a new formulation in the code. We have realized that if we're talking about plain bars anchored in the bottom cast positions, so in good bond cast position, some codes of practice in the past, for example, in UK also, but also in Italy, can be on the safe side. While, especially if we have a concrete correlation of among 2.53, while it's just the opposite if we talk about top cast bar in the bad cast position, well, where there is the codes of practice are not on the safe side. The past rules of the codes of practice cannot be on the safe side. So it depends on the case.
Yeah. Okay, thank you. Let me check the next question. I think it is for you, Alan. In the beta factor calculation, you mentioned the consideration of failure type of an element, ductile failure versus brittle failure. Is redundancy also considered in the beta calculation? And how do beta captures the implied reliability for single path elements?
Okay, so you're right. In the case of the safety levels that I indicated, which are component level safety, we're looking at alternative safety failure modes. So we can have ductile failure modes with remaining capacity through ductile failure mode without remaining capacity through brittle failure mode, where we specify the highest target beta level associated with that. I think what you're talking about in the context of redundancy is whether we perform a system reliability analysis on the structure, which is something which we can do. It's not in terms of the values which are specified there. We would need to specify a particular value for the system analysis which we perform.
Okay. There is a question I think that we will address in the next webinar. It's regarding the reliability update. Do you have any experience or comments on using monitoring inspection data, not under proof load testing, but normal traffic load to update the reliability? So I think it's more bridgeway in motion that we will investigate during the next webinar. But Alan, you can
just to come in on that, there is a new task group, IABSE task group 1.10, which is focused on exactly this issue on using traffic data or available way and motion data for assessment of existing structures. So I would encourage you to visit the IABSE website and maybe reach out. I'm chairing that task group. We'd be delighted to interact with you further on that.
Yeah, very great opportunity to continue this work. Yeah, very good. Let me check the question. The questions are coming now. Yeah, a question by Francis McNeon. For the concrete sampling for Danish Bridge to prove the strengths, 12 samples were taken. Were these at the critical locations? And is there a minimum number to be statistically significant? Yeah, Alan.
So were they taken at the critical locations? When we do take samples from an existing structure, we try and stay away from the critical locations. So no, they're not taken. Fabrizio indicated the kinds of conversions which we consider if we aren't at a particular location, at the critical location in the structure. And also there are minimum required numbers of tests that we need to be performed to be statistically significant, and we determine those before we perform the testing.
Mm-hmm. Another question from Francis. I think maybe Fabrizio, you can address that. In UK, for substructures and retaining walls, a qualitative analysis is permitted. Often, analytical approach would indicate failure. My understanding is that the qualitative approach will still be permitted. So I think you mentioned that in your presentation in the next generation of Eurocodes with this qualitative assessment.
Yeah, it will be. In general, it will be permitted by the Eurocodes, but it's subjected to the national annex. So the national authority will decide where, in which cases, qualitative assessment methods can be used as an alternative to quantitative assessment methods.
Yeah. Question by Meta Sloth to Alan. Notice that the model uncertainty in all cases are very important for the result. Sure. Refer sensitivity analysis shown. Any concern about that? I remember that the model uncertainty specified in the Danish guideline is based on an NK-based bulletin. Has the probabilistic model for model uncertainties in the guideline been revised or updated?
Hi, Meta. Nice to hear from you. What I would say is that, yeah, I'm always concerned about the values of all the variables when I look at them at the beta point. That's why we perform the sensitivity analysis as well, to see if we're close to the target value, how sensitive the results would be to the modeling that's been performed. And yeah, Joan Rhodesgore has done an awful lot of work looking at updating the modeling of the format for modeling of the model uncertainties in the new version of the guideline, which is coming out. So stay tuned.
Thank you, Alan. Yeah, one question more by Christian Keynes. Dear Alan, thank you very much for your presentation. I want to ask about the conversion of the characteristic traffic load models from the codes to mean values for the probabilistic calculation. Did you perform traffic measurements so you obtain the values, or are they derived from the codes? Looking at it from the regulation aspect, the non-variation coefficients from literature may not necessarily be the same as used in the codes. What is your opinion and how to treat this uncertainty? How have you done it?
So first of all, Christian, thank you for the question. In the context of the assessment as performed according to the guideline, it's a prescribed load case, which considers the 100-ton vehicle beside the 50-ton vehicle. And again, in the updated version of the guideline, both a 50-ton permit vehicle and the legal weight limit vehicle are modeled. So those values are very tightly prescribed in terms of the mean values and the coefficients of variation. Your question is a very good one, though. And again, if I can plug task group 1.10, this is something that we're looking at, is using way and motion data in order to characterize the statistical parameters of the traffic data which we use in determining the reliability levels of the structure. So I'd be happy to I think we're nearly out of time. I'd be more than happy, Christian, if you want to send me an email and we can talk further about this, and I'll keep you involved in the work that we're doing in task group 1.10.
Thanks, Alan. You still have one question. Should the probabilistic method, so the question is by one, should the probabilistic method be called semi-probabilistic, given that the demands and capacities of elements are calculated deterministically with direct formulas and no joint probabilistic distributions?
Okay, so Juan, maybe there's a confusion here in that the deterministic method is used to determine what the critical limit state is for subsequent modeling in the probabilistic assessment. So we do model the probability of capacity based on the considered variables around material strengths and so on in the probabilistic analysis.
Yeah. And semi-probabilistic is the format for when you use partial factors. This term is used for this. A question by Lin Wan Wender: can these guidelines be applied to timber or timber steel, timber concrete hybrid bridges? I think the question is for the reliability approach, the probabilistic approach.
So I might come in again, and maybe Lynn is referring to some of the failures that they've had in Norway around timber structures. So in general, the principles can be applied, but the specific characterizations of timber statistical properties and around the particular limit states would have to be very carefully considered.
Yeah. We can still have one question the audience wants. Yeah, thank you, Juan. The webinar is recorded, so if you want to check after this, after today, all the presentations will be made available on the IABSE website. I think now it's time to close this webinar. I would like to thank all the speakers for their very interesting presentations about this important topic of assessment of existing bridges. Thank you to the audience for participating today to this webinar. And do not forget, there is a second webinar on June the 9th, where we will look at all the case studies and we will show how we apply different verification formats. We'll hopefully see you there. And for now, I wish you a very great weekend. And thank you again for attending today. Bye-bye.
Thank you. Bye. Bye-bye.
Thank you. Bye-bye.